Welcome to Edisler. Today we're diving into the fascinating world of quantum mechanics. Get ready to have your mind blown by these 10 lesser-known facts about the quantum realm. From particles existing in multiple states at once to the strange influence of observation, the quantum world challenges our everyday understanding of reality. You might have heard about Schrödinger's cat, but have you ever wondered how particles can tunnel through barriers, or how two particles can remain connected across vast distances? Each fact we discuss will take you deeper into this bizarre and fascinating world, making you question the very nature of reality itself. So buckle up and prepare for a journey through the quantum realm. Let's get started with the first mind-bending fact about quantum mechanics. Imagine a marble rolling towards a hill. In classical physics, if the marble doesn't have enough energy, it will never make it over. But in the quantum world, particles can tunnel through barriers they theoretically can't overcome. This is quantum tunneling. It's crucial for modern electronics. Flash memory and semiconductors rely on it. Enzymes use it to speed up reactions. Quantum tunneling challenges classical intuitions and advances technology. Quantum superposition is one of the most famous and perplexing concepts in quantum mechanics. It states that particles can exist in multiple states or positions simultaneously. Imagine flipping a coin and instead of landing heads or tails, it exists in a state of both heads and tails until you observe it. This is the essence of quantum superposition. A classic thought experiment illustrating this is Schrödinger's cat. In this scenario, a cat inside a sealed box is simultaneously alive and dead until someone opens the box and observes it. Quantum superposition forms the backbone of quantum computing. Unlike classical bits, which can be 0 or 1, quantum bits or qubits can be both 0 and 1 simultaneously. This allows quantum computers to perform many calculations at once, vastly increasing their computational power compared to classical computers. The delayed choice experiment proposed by physicist John Wheeler takes the strangeness of quantum mechanics to new heights. This experiment suggests that decisions made in the present can influence events in the past, turning our conventional understanding of time on its head. Imagine you're conducting a double-slit experiment where particles pass through two slits to create an interference pattern. In the delayed choice version, you decide whether to observe the particles' paths after they've already passed through the slits. Astonishingly, your choice seems to retroactively determine whether the particles behaved as waves or particles. This experiment implies that the quantum world doesn't solidify into a definite reality until it's observed, even if that observation occurs after the event. The delayed choice experiment has profound implications for our understanding of reality and time. Next, quantum entanglement. Quantum entanglement is perhaps one of the most mind-boggling phenomena in quantum mechanics. When two particles become entangled, their states are linked in such a way that the state of one particle instantly influences the state of the other, regardless of the distance separating them. Albert Einstein famously referred to this as spooky action at a distance. Imagine two entangled particles, one on Earth and the other on the Moon. If you measure the state of the particle on Earth, the particle on the Moon will instantaneously assume a corresponding state. This happens faster than the speed of light, defying the classical notion that information cannot travel faster than light. Quantum entanglement has been experimentally verified numerous times, including the famous Bell test experiments. These experiments have shown that entangled particles exhibit correlations that cannot be explained by classical physics, supporting the predictions of quantum mechanics. Chapter 5: Quantum Xeno Effect. The quantum Xeno effect is a fascinating phenomenon that highlights the peculiar role of observation in the quantum world. Named after the ancient Greek philosopher Xeno, it suggests that a quantum system can be frozen in its state through continuous observation, akin to the adage, "A watched pot never boils." Imagine you have an unstable particle that's supposed to decay over time. According to the quantum Xeno effect, if you continuously observe the particle, you can prevent it from decaying. This effect has been experimentally demonstrated with unstable particles, showing that frequent measurements can indeed halt their evolution. In the quantum realm, the act of measurement collapses the wave function of a system, forcing it into a definite state. Continuous observation effectively keeps the system in that state, preventing its natural evolution. This phenomenon has practical implications in quantum computing and control. Chapter 6: Wave-particle duality. Wave-particle duality is one of the cornerstones of quantum mechanics, illustrating the dual nature of particles. At the quantum level, particles such as electrons and photons exhibit both wave-like and particle-like properties, depending on how they are observed. The double-slit experiment is a classic demonstration of wave-particle duality. When particles like electrons are fired through two slits, they create an interference pattern on a screen akin to waves overlapping. However, if you observe which slit the particles pass through, they behave like individual particles, and the interference pattern disappears. This duality challenges our classical understanding of particles and waves as distinct entities. In the quantum world, particles are described by wave functions that encapsulate their probabilistic nature. Depending on the experimental setup, these wave functions can manifest as either waves or particles. Wave-particle duality has profound implications for our understanding of the universe. Zero-point energy is a fascinating concept in quantum mechanics, referring to the lowest possible energy that a quantum system can have. Even at absolute zero, when all classical motion ceases, quantum systems still possess this residual energy due to the Heisenberg uncertainty principle. The Heisenberg uncertainty principle states that certain pairs of properties, like position and momentum, cannot be simultaneously known to arbitrary precision. This inherent uncertainty gives rise to zero-point energy, ensuring that quantum systems are never completely at rest. Zero-point energy has significant implications for our understanding of the universe. It contributes to the cosmological constant, which is responsible for the accelerated expansion of the universe. The energy density of a vacuum, filled with zero-point fluctuations, plays a crucial role in cosmology. The concept of zero-point energy also underscores the quantum nature of the vacuum. The quantum foam. Quantum foam, also known as space-time foam, is a concept that describes the chaotic, fluctuating nature of space-time at incredibly small scales, close to the Planck length. Proposed by physicist John Wheeler, quantum foam suggests that space-time is not smooth and continuous, but rather a turbulent, frothy sea of quantum fluctuations. At the Planck scale, the effects of quantum mechanics and general relativity become intertwined, leading to a highly dynamic and uncertain nature of space-time. Quantum foam represents the idea that space-time itself is subject to quantum fluctuations, with tiny, transient wormholes and bubbles constantly forming and dissipating. This concept has profound implications for our understanding of gravity and the structure of the universe. It suggests that at the smallest scales, space-time is far from the smooth continuum described by classical physics. Instead, it is a seething, ever-changing landscape shaped by the principles of quantum mechanics. Quantum gravity. Quantum gravity is one of the most challenging frontiers in modern physics. It seeks to unify general relativity and quantum mechanics. General relativity describes gravity as the curvature of space-time. Quantum mechanics governs particles at the smallest scales. Reconciling these theories is a formidable task. Proposals include string theory and loop quantum gravity. Chapter 10: Quantum computing. Quantum computing harnesses quantum mechanics to perform calculations far beyond classical computers. At the heart of quantum computing are qubits, which can exist in superpositions of states. This allows quantum computers to perform many calculations at once. Quantum phenomena like entanglement and tunneling solve complex problems. The potential applications of quantum computing are vast and transformative. Thanks for watching. If you enjoyed this video, don't forget to like, share, and subscribe to Edisla for more mind-blowing content. Let us know in the comments which quantum fact surprised you the most. Quantum mechanics continues to challenge and inspire us, revealing a universe that is far more intricate and interconnected than we ever imagined. From quantum tunneling to quantum computing, each phenomenon offers a glimpse into the profound and mysterious nature of reality. As we venture further into the quantum realm, we'll continue to uncover new insights and applications that have the potential to transform our world. Until next time, keep looking up and stay curious.